Okay, I think it's time to make a start. So I hope you all had a nice break. I'm not sure if you had a chance to look at quiz number 1, but it would be good if you could have a go of that, because that gets you used to doing the kind of questions that you'll need to know how to do. Yeah, and this is just a reminder. I want to make sure you all have enough time. Assignment 1 is due on the 18th of October. It's already up on e-learning. If anybody has any trouble seeing it or any questions, something doesn't make sense, just feel free to ask me anything by email. That's fine. The assignment 2, of course, is not up yet, but I just give you the deadline for when that one will be due. This Friday, October the 5th, in the tutorial, which will be in Lecture Theatre 2, sort of up there, the tutor will be going over the quiz, number 1. Yes?
Sorry, I'm sure this is already been explained, but can I just double check
Sure.
that the quizzes are just purely for
That's exactly right, yes. Yeah. So the tutor will just go over them, you know, over all the solutions and take any questions. And any other questions, doesn't have to be about the quiz. So that's on Friday. All right, so let's try and remember where we left off. I think the last time we kind of derived the reciprocal of the simple cubic lattice. Because this is kind of a really important thing, I'm just going to start you off a little bit on how to find the reciprocal lattice of the body-centered cubic 1. So the best coordinate system to use is like this, actually. And it's good to get used to drawing these things. You know, if you stay on in this kind of area, it'll be something that you kind of sort of do a lot. Okay, so that's, first of all, you need to find your coordinate system, and we want to kind of draw our body-centered primitive lattice vectors. So now I'm going to try and draw this, you know, in an understandable way. So body-centered cubic is what we've got. So it's a little bit of an unusual way to draw it, but there's one cube, okay? There's one conventional body-centered cell, and in the middle there's an atom, of course, okay? And there's another one sort of coming out at you like this, and there's an atom there, atom there, atom there, atom there, and of course there's one in the center, okay? And the final one, you need your 3 vectors A, B, and C. There's another cell coming out at you sort of from the front area, which I'm trying to draw now. Atom there, at all the corners of the cube, and of course one in the body-centered position, and yeah, one on the origin. So the best vectors are these ones here, from the origin up to the center atom of that cell. We call that A1. A2, from the center up to the center atom of that cell, call that A2. And the last one, you can probably guess, A3 coming down like that. So, you know, we've been given the relationship to be able to derive our reciprocal lattice vectors, and we'll write that down in a minute. But let's first of all, the first step is you need to write your primitive vectors here. So we have A1 is A over 2. Okay, A being the lattice constant, so let's make sure everyone remembers where that is. That's the length of the conventional cell, okay? And so what we're now doing is getting the coordinates of the primitive vectors. So A on 2, and then we've got a component in every direction along the positive y, along the negative x, and the positive z. So we have negative x hat plus y hat plus z hat for our A1 vector. For A2, you can sort of see here, you're going to have A2 will be the same prefactor, but x coming out at you, so positive x minus y hat plus z hat. And the final one, A3, A on 2, positive x hat, positive y hat, and negative z hat. So these can be your primitive vectors for the body-centered cubic cell. And remember, so you need to find, I'm not going to do it all for you, but you can do it later on for homework in your spare time. So find the reciprocal, how do you spell it? Start again. So find the reciprocal lattice of the body-centered cubic. So we need to recall B1 is equal to 2 pi A2 cross A3. Remember that? On A1 dot product A2 cross A3. And B2, similar, but the top part's different. We have a 2 pi again. You have to be a bit careful here. So it's A3 crossed with A1 over the same thing. And I'm going to call the denominator just V, because this is just the volume of the box or the cell. Okay? And then your other one, B3, is equal to 2 pi A1 cross A2 over, say, the volume. Okay, now so you go and do all of that stuff. And remember, you know, with your dot products, you know, A1 dot A2, remember all of that? Because of the angle between them and the cross product, however you want to do that, sine of the angle between them. And what you should get is B1, 2 pi over A, z hat plus y hat. So that's your first vector. And we'll plot it out and make sure it, you know, see what shape it does give us. B2. B2, again, is your 2 pi over A, z hat plus x hat, and B3, 2 pi over A, x hat plus y hat. So it's sort of complicated when you're doing it, but it comes down to some, you know, quite nice vectors there, reciprocal lattice vectors. So, you know, let us plot that and see what it looks like. Just make sure what it looks like. So again, let's see what it's given us. X hat, y hat, z hat. In this case, we can just consider a cube, which I'll try and draw somehow. Is that good? That's all right. So here's our origin. And let's draw B1. Where is B1? It's got Z and Y. Z and Y. And it's half 2 pi on A. And the 2 pi on A is here. This is 4 pi on A. So it points to, make sure I get this right, points to here, because that's a half Z and a half Y. Okay, so that's our first B1. B2 is Z and X. So the B2 points here, to the middle of this side here, B2. And B3 is in the X and Y plane here. Okay, there we are. So, I don't know if you remember, but these vectors and this geometry is exactly the FCC primitive cell. Okay, so these are just the FCC primitive vectors. So I think, as I said before, the leaving off last lecture, the reciprocal lattice of the BCC is the FCC, and the reciprocal lattice of the FCC is the BCC cell. And we just focus on these because these are, the more simple ones. There's also hexagonal, which I'll mention shortly. Okay, so I think that's pretty straightforward. I'm turning you back now. Yeah, so we've done this first one and the second one. Now the third one is start off with the FCC. So start off with those vectors that we just derived, only in real space, and you can show that that is the body-centered cubic. I think I've already put that down for, maybe it's a question on your assignment or on your quiz, I'm not too sure. But make sure you're kind of familiar with those kind of things. Okay, so now we're going to introduce the concept of the Brillouin zone. So what is the Brillouin zone? Remember how when we were dealing in real space, we defined the Wigner-Seitz cell? And so the first Brillouin zone is just like the Wigner-Seitz cell in real space, except it's in reciprocal space. Okay? So the Wigner-Seitz primitive cell, if you have here the BCC, the Wigner-Seitz, the first Brillouin zone is just that of the FCC Wigner-Seitz cell. Conversely, the reciprocal, we know the reciprocal of the FCC is the BCC. So the first Brillouin zone of the FCC lattice is just the Wigner-Seitz cell of the BCC. And that is the first Brillouin zone. Hopefully that's not too confusing. So the first Brillouin zone is just like the Wigner-Seitz cell was in real space, except it's in reciprocal space. Remember how we made it? We'll show you in some more slides how we actually make the cells. But in three-dimensional, this is what they actually look like. We had last lecture very simple squares and so on. But in three-dimension, they had those shapes. So let's go back again simple. I'll just show you one other thing that will come in handy later on. This is the Brillouin zone of the BCC, okay? And within this shape that was there, we defined some high symmetry lines and high symmetry points. They are, by convention, given names like the X point. There's another X point because it's the same. And you have the K point here, which is on the side of this sort of hexagon. L point is in the center face of this hexagon. And so when you look at electrons in crystals, very often when we plot the band structure, which we'll go into a bit later on, you can plot the band structure along these high symmetry lines. Okay, we'll show a plot later on. So, in reality, the electrons are occupying, space in the crystal, but we normally present that as cuts through the Brillouin zone and along high symmetry lines. That's just getting ahead of ourselves a little bit, but it's good to put this into your mind already. Okay, so let's go back a little bit, start off a bit more slowly. This now is not a real lattice, it's in the reciprocal space. These are your reciprocal lattice points, these things here. This shaded area is your Wigner-Seitz cell, what we called the Wigner-Seitz cell, but because it's in reciprocal space, we call it the Brillouin zone. this is called the first Brillouin zone. And, we are drawing it around the center black point. Remember, it was the shape that, for any position in this shape, it is closest to the center point than to any other of the lattice points. And remember the way we created it? We drew a line bisecting the nearest neighbor, and where all those lines intersect, that's the way you created the Wigner-Seitz cell. Everybody clear about that? Another thing I should add here is that in reciprocal space, these lines that cut these reciprocal lattice points are also called Bragg planes. And we'll get onto that when we do a bit of scattering. Okay? So the lines that bisect these reciprocal lattice points are scattering planes. So just like we did before, you can go to the second Brillouin zone, if you like, or the second Wigner-Seitz cell. So this was our first one, remember? And on the next slide, I'll show you how we got the next one out. But these triangles here are the second Brillouin zone. Okay? And you can also think of the Brillouin zone as being, the second Brillouin zone is the set of points that can be reached from the first zone. Okay, here we are in the first zone. We can reach the second zone by crossing one Bragg plane. Okay, if you're here, you cross, this is a Bragg plane. You're only allowed to cross one, and there you are. You're here, cross this one, and you are in this second Brillouin zone. Okay? And you can go third, fourth, fifth, and so on. And so if you go to the nth Brillouin zone, it can be defined as a set of points that can be reached from the origin, remember, we're in the middle, but by crossing n-1 Bragg planes, and then you'll end up in the nth Brillouin zone. So let's just have a look at the second one. The second one is the green area, and it's, remember, it's very much like we did with the Wigner-Seitz cell last lecture. Okay, to get the green one, you start at the origin, you go out to the next nearest lattice point. Next furthest away are the green ones. You put a line bisecting the green point to point, and then another perpendicular line over here, another one here, and so on. And then you generate that green shape. Is that clear? I think it's clear. You let me know if it's not clear. And we can go to the third one. The third Brillouin zone is the yellow area. So we've done the first one by going to the closest reciprocal lattice points. We've done the second one by going to the second most close reciprocal lattice points. The next one is here, okay? Or out here, if you like. So again, from here to here, we put a line, and that gets you this line here. The same thing down here, they get you another line here, and so on. And the shapes that are closest to the center point get you that yellow region. And further out, you would get the purple areas, and it gets too complicated to be really useful, okay? So normally what people do, they actually don't, you can fold all those points back into the first zone. So really we only want to be concerned with the first Brillouin zone because all the physics can be folded back into it, okay? So you don't really need to, I just want to make sure that you're aware of how this is defined and what it is. Okay, so coming back now to a bit more reality. Some of these slides are a little bit repetitive, but it doesn't hurt. It drums it into your head. Okay, so basically, again, this is the body-centered cubic. In reciprocal space, we saw it generated an FCC lattice. Okay. These, you will know, If you don't remember them, doesn't matter. They'll be in a formula sheet in your exam anyway. Okay? So, and you know, people do spend time, you know, actually generating these shapes. This is just the first 3 here. So remember, we've just dealt with these 2 in 3 dimensions. I showed you what it looked like. If you go to the second one in 3 dimensions, you know, they get really complicated. This is like the outside of the contour of the second Brillouin zone that we saw in 1 dimension. And again, third Brillouin zone for the BCC and the FCC lattice. And yep, okay. I actually wanted to show you something else. I don't know why it's not in my slide, but I can show it to you. Let's see. Yeah, so this just to show you that this is quite a recent paper, 2017, where you know, someone has developed some software for visualizing these surfaces up to any dimension that you like. This is just to show you that it's kind of interesting. I don't know exactly what they're going to use it for. I'm sure in some fields you do need to know about these, and you may use them. But we don't need to concern ourselves with the higher order ones in this course at this present time. All right. So, as I mentioned, you know, the hexagonal is another very common kind of crystal structure, and it's important that you, see how that works in the reciprocal of that lattice. So, I've just put a little bit of a summary here. In reciprocal space, the lattice constant of the reciprocal lattice becomes 4 pi on root 3a. And 2 pi on c. Remember, the hexagonal lattice has got c in the upward direction, and in the planar it has a in the real space. In the reciprocal space it has those 2 dimensions. And when you do that reciprocal lattice formula, you'll also find that there's rotation about the c-axis of the in-plane vectors. And I think that is in your assignment. So, yeah, you can work yourself through that. I think it won't be too hard. It's all over the web anyway. So, but it's important that you learn how to do it. Okay, so a couple of definitions here. Coming back now to real space. Okay, what do we mean by a lattice plane? We're going to sort of introduce some notation to define lattice planes and directions now. So there's 2 ways you can think about it. There's probably more, but one way is it's a plane containing at least 3 non-collinear points, and thereby an infinite number of points. Okay, so it's like, imagine a 2-dimensional sheet. It's got points all over it that extend forever in both directions. Or you might like to think of it as, okay, a family of planes equally separated, like you could draw them here, right, which taken together, it will cover all of the points in your lattice. Okay, so every atom will be, say, on one of those planes, if it's a true lattice plane. And you can imagine there's many sorts of planes that you can have. 2 simple ones are given to you there. Yeah, and for more information, background reading, there's always a big explanation in Ashcroft. And I think also in the Oxford Basics book as well. A little bit more. Okay, now this is another important thing here. So there's a picture of our lattice. We've got some planes. These, as we'll see later on, are called the 1, 1, 1 plane in curved brackets. We'll see that later on. And if you define a distance d for the spacing of these planes, then there will be a reciprocal lattice vector that is perpendicular to the planes, and it has a length of 2 pi on d. Okay? So if you're in real space and you've defined some lattice planes with certain spacing, whatever that spacing d is, there will always be a reciprocal lattice vector that points perpendicular to that plane and with a length 2 pi on d. Conversely, okay, now we're in reciprocal space. For any reciprocal lattice vector G, and remember the reciprocal lattice vectors always land on points of your reciprocal lattice, there will be a set of lattice planes, okay, in real space that are normal to G. Okay, so if I've got a reciprocal lattice vector starting from some lattice point going to some other lattice point, there will always be in real space a set of planes perpendicular to that lattice vector. Okay. Yes. It may be noted here that if your lattice plane is D, then the shortest reciprocal lattice vector will be 2 pi on d. So it's the shortest reciprocal lattice vector, not any old reciprocal lattice vector. Because if you choose the shortest or the smallest plane spacing, then you will get the shortest reciprocal lattice vector. Okay. What else? Okay. Now what we want to do now is introduce the concept of Miller planes. Who's familiar with Miller planes? Yes, okay, so you can probably go to sleep. That's okay. Let's define them. Okay, so what we want to define, Miller indices are normally indicated by HKL, and they define a particular plane, and they also define a particular direction in our crystal system. They are integers, the HKL are integers, and they have no common factor. And so if we have a plane with Miller indices HKL, and I'll demonstrate this later on, we'll do an example, then there will be a reciprocal lattice vector perpendicular to it that has these B1, B2, B3 are your reciprocal lattice vectors, and the coefficients will be H, K, and L. Okay, so for a given plane, there will be a reciprocal lattice vector perpendicular to it with these coefficients H, K, L. Okay, I think an example is always good. So what you can see here is part of a crystal lattice. You know, obviously there's atoms all throughout here in 3 dimensions. But this explains how to determine what the Miller indices are for a given plane. Now, our plane of interest is drawn there, and we want to know how to label it. So what are the steps to label it? Okay. First, look here. This is A1. So this is, if you like, kind of the X direction. It's a bit unusual. The Z, or the A2 direction, is vertical. Okay. And the A3 vector is sort of out here towards the left. So the first thing you do to define or determine your Miller indices are to figure out where this plane cuts your axis. Okay. Step 1, determine the intercepts with the axis in units of the lattice vector. Okay, so let's look at this one here along the x-axis, if you like, the A1. So 1, 2. It is of length, or it cuts at 2 in the A1 direction. In the A2 direction, it's just 1. And in the A3 direction, it's 2. Okay, so step 1, in the X, Y, Z, or A1, A2, A3 directions, we have 2, 1, and 2. Okay, and the second step, we take the reciprocal of each of these numbers. So the reciprocal, you get a half, 1, and a half, but that's really messy, and it's not in the proper notation yet because they have to be integers, remember? So we want to find the smallest integers such that we keep the ratio the same. And if you just multiply through by 2, you will end up with your Miller indices. Okay, so it's like a recipe. You don't need to just remember how to do it, and you'll always get the correct plane. So this plane here is given the Miller indices 1, 2, 1, H, K, L. Okay? This kind of just says the same thing, but I like the one that I had before, so yeah, I'll just skip over that. Here are some examples, and we'll do one together again, just to get it into your head. So this here is very simple and common, plain. Okay, it's the 0, 1, 0. You've always got to make sure you know which is the X, Y, and Z, or you know which direction. I don't always put the Z up there, right? So here you've got the A, and the B, and the C. Let's have a look at it. First of all, look at the intercepts along the A. Okay, well, there's no intercept. This plane will never cut this axis. Okay, so you put infinity. Along the B, boom, you've got one at, yeah, it's obviously at 1. Okay, one lattice vector. So you get the 1 here. Okay, and then you're coming out here again. This plane will never cut it. So you get infinity. Now remember, turn them upside down. So you get 1 over infinity, 1 over 1, 1 over infinity, and you get 0, 1, and 0. And so this is the labeling of this plane. Okay, this is a very common kind of plane here. Often they put this as a z-axis, and it would be 0, 0, 1, but that's how you get it. This case here, kind of similar, exactly the same, only now this position is at half. Okay, and we turn it upside down, so this would be labelled 0, 2, 0. Some more really common lattice planes or Miller indices. Okay, I don't know if you've seen all these. This is just like we had before, paying attention to the kind of different notation here. This is like a 1, 1, 1 plane where it's sort of like lying across the diagonal, but only in the X and Y. And here it's leaning, like tilting to the corner of the cube. Okay, this is a classic 1, 1, 1 here, and that will make a hexagonal structure. If you would take this plane and extend it in in 2 dimensions, then you would end up with a hexagonal plane of atoms. Okay, now, as you can guess, a few more examples for you. So I want you to make sure that you understand these kind of things and just how to get them. Just, find where it cuts, turn it upside down, reduce it to the smallest integers. Okay? These are all very common. In this case now the z-axis or the c-axis is up here. This is a 0, 0, 1, 1, 0, 0. I won't bother listing them all. But yeah, make sure that you kind of get this. Here, looks a bit messy, but there's actually 2 planes that fit into this cell, right? 1, 1 bar 1 is this triangle here, and coming further out, there's another plane that cuts into the cell here. The same thing here. It's a little bit hard to see. Anyway, I'll let you try and think about that, okay? Yeah, the bar on top is normal convention in this area, so instead of writing a -1, you just put the bar on top. Okay, so I think you all get the idea, but nevertheless, I'm going to try and make sure you do. So here we've got our nice question that's been given to you. Find the Miller indices of this this cut here. So Okay, let's first of all make some decisions about axes, okay? You can't, okay, this is, yeah, sorry, this is obviously the x, and this is the y, and this is the z, because A, B, and C. Fine. So, find the intercepts along the A, B, and C directions. Okay, what is it along the A? Come on. 3? Yes. Along the B? 2 and C? 2. Okay, good. So now we've got to take reciprocal. So this will become 1 over 3, 1 over 2, 1 over 2. But we don't like that. So what is the smallest set of indices that we can... Oh, sorry. You should tell me. So what is the smallest set of integers that keep that ratio? Any ideas? I heard somebody... Yes. Good. H, K, L. That's a bit messy. Yeah, good. Okay. So, yeah, this plane is labeled 2, 3, 3 plane. I'm going to do something while I'm here, but you haven't quite learned it yet. You'll learn it maybe the next slide. But, or should I wait? No, I should probably not do it. Don't want to confuse you. So that's good. One more example, just to make sure you cannot. What's happening here? Help. It won't go away. This will not go away. This is not funny. I don't want that. Oh my gosh, what am I going to do? I could restart the whole thing. How much time have we got? You see, I'm putting it on the computer, and yet the visualizer is still showing the visualizer. So, if it's so set on showing itself as the visualizer, then fine. She'll do it. She'll go with the visualizer. Well, I could reboot the whole thing, but I'm afraid it might just take a bit of time to... No, I'm going to have to reboot because it's not even paying attention to what I've got there. I'm sorry. I'm going to have to shut it down. finally. Sorry about that. Thank you for your patience. Yeah, okay, this is just one more example, and I think you will all be kind of sick of it. Okay, here you are given another plane that you have to identify the Miller indices of, A, B, and C. The procedure, identify the intercepts, 1, 2, 2 here, along the B-axis, 5, 1, 2, 3, 4, 5, and C, 2. Turn them upside down. You get a half, a fifth, a half. Then you find the smallest integers that keep the same ratio. And in this case, you can multiply by 10, and you get 5, 2, 5. So this is your Miller plane. Okay? Great. And you know that there will also be a reciprocal lattice vector perpendicular to this plane here with the vector 5 in the B1 direction, 2 in the B2 direction, and 5 in the B3 direction. Okay, another interesting thing is if you've got a hexagonal lattice, what people normally do is the following. If you've got a hexagonal lattice, you're looking down on the plane, okay, and you've got the c-axis coming out here. If you just label it by the usual Miller indices notation, you will end up with this plane being called the 1, 0, 0, this one being the 1, 0, 1, 0, and this one being the 1, 1 bar 0. Now, people don't normally like that kind of notation. It's normally like to have, because all of these planes are the same, you know, by symmetry, they're just the sides of, you know, this hexagonal cell. So what they do is introduce another axis, in this case the u-axis, see? You've got the x, you've got the y, and the u. And they introduce another indice, okay? So how is that indice figured out? You have your h index, your k index. This is the new one, I, which will go in here. You'll have 4 indices, h, k, I, and l for hexagonal lattice. And you'll figure out what value the I has by this equation here. H plus k plus I has to be 0, okay? So you, for example, if you want to rename this plane, the 1, 0, 0 plane, in this new terminology, you know that h is 1, you put it in there, k is 0, you put it in there, and you will figure out that the I will have to be equal to -1, okay? And that's how you get this number here, 1, 0, 1 bar 0 is just the 1, 0, 0 plane that has been renamed using these 4 indices. Okay. So I'm just going to make that a tiny bit clearer because this can be a bit annoying sometimes. If I'll put it over here.
Is
U is flat. Yeah. I'm going to try this thing again. Hope it doesn't glitch me up. But, all right. So yeah, this is what we did. We have in our 3 indices 1, 0, 0. We want to put it in our 4 index notation. Remember, h plus k plus I has to be 0. We are given h and k, 1 and 0. Therefore, the I has to be -1. And h, k, I, l, this becomes 1, 0, 1 bar 0. Now I'm going to do another one, okay, because 1 is not enough to look at 1, you've got to look at 2. So in this case, we want to rename this one. We don't like this one. We want to rename it into the 4 index notation. We know h is 1, h bar is -1. So 1 plus minus 1 plus something has got to equal 0. This already goes to 0, so I is just 0. So HKIL just becomes 1 bar 0, 0. So this is what these four digits are. So when you're looking into the literature and stuff, sometimes you'll see some have 3 milliindices and some have 4, and you think, what is this fourth one? And that's what it is, and that's how you get it, okay? Yeah. Let me just see. So that was important. Oh, there's one other important thing. Yes, I think I've got time to do it. I better put this back up. Okay, this is another thing that is important, the spacing of the planes. How do you work out the spacing of the planes? Here's a little section of a plane up here. O to N is the interplanar spacing. So here's O, here's N. So if you can imagine, there's obviously another plane here, right, that cuts through O. So if we just get... so this is in real space, this is the Miller indice. Cos of this angle gets you to this is a perpendicular. So we're making the perpendicular. Remember, D is the spacing between planes that's perpendicular to the planes. So we just get OA cos of alpha is basically equal to, so this is just cos, okay? You go through here, you get cos, and that's equal to your D, your interplanar spacing. If you get time, you can just make sure that you are happy with that. And then you just do the same thing for the other axes, the B and C axes. You know, you can call them different things, it's an alpha, beta, gamma, okay? Just keeping it general, doesn't have to be a cube, right? We've got A, B, C, so it could be orthogonal. They're not equal yet, the A, B, and C. And we know that if you've got orthogonal axes, you have this relationship between the angles. Okay, that's just trigonometry. You can sort of look that up and verify it. Cos squared plus cos alpha squared plus cos beta squared plus cos gamma squared equals 1. Then you just substitute, you know, what you have for cos alpha, beta, gamma, and just collecting them all up. And if you want to say we've got a cubic lattice, you make it really simple, you put all of these to be the same, then you end up with this expression for being able to find the interplanar distance if you are given the Miller indices. Okay, so that's a really nice way of being, you know, the relationship. Here, I mean, you keep it like that if you've got a, you know, sort of rectangular orthogonal kind of lattice. These A's and B's and C's, you know, A might be equal to B but not C and so on. So this is like a general kind of one, but for the special case of cubic you have that relationship there. So you use that to find the interplanar spacing if you are given HKL. Okay? And of course, yeah, the lattice constant, A. How are we going for time? Okay, I should stop, but I'll just do one more thing. Convention. You know, these curved brackets are from Miller planes. Instead of writing, they're all equivalent. For example, you've got a cubic, 1, 0, 0, you know, they're just like sides of the cube, right? And as a family, you refer to them as just the 1, 0, 0, and you put curly brackets around. I'm not sure if chemistry does it different or whatever, but this is the normal crystallographic way, I think. Curved brackets, planes, curly brackets, families, and later on, we'll just start off again on Friday, directions. Remember, we had a plane, and there was a direction perpendicular to the plane. That will have square brackets, and the family has pointed brackets. Okay? But we'll go over that again. I better stop here. Please come on Friday and yeah, go over the quiz and yeah. And then you'll get another quiz.